All right. Good morning, everybody. So, as I mentioned in the chat, today we'll wrap up our discussion about integration by parts, and then move on to section 8.2, which is integrating powers of trigonometric functions. But I guess some of you guys sent me some questions about integration by parts, so we'll go over them. And it seems that they have a very similar questions. So, yeah. And I want you to at least be comfortable with integration by parts before we go on to the next section, because in the coming sections there are very different techniques of integration. And unfortunately, well, I think this is one of the difficulties of the exam for this chapter, is that you will just be given the integrals, and there is a big chance that you will not be told what specific method to use. So you will have three or four or five choices. So you need to be able to distinguish what method applies for a particular integral, right? So for integration by parts, we said that it is particularly helpful if you are integrating a product, right? A product of the form u dv. And Formula 1 tells us how to do this integration by parts. So if you have the integral of u dv, you need to choose what factors in the integrand will go into the u, right? And what function will go to the dv. As a general choice, the function that you choose to be u should be easily differentiable, and dv should be easily integrable, because we will need both v and du in formula number 1. And your hope is that this integral, the integral of v du, should be much easier to integrate than the original integral u dv, right? So aside from having that very general criteria, we have this mnemonic which tells us the order of precedence for choosing the u. So the choice for u um, should go like this in hierarchy. The priority would be the inverse trig functions, next the logarithmic functions, algebraic functions, trigonometric functions, and exponential functions. This is a general guidelines which works most of the case, but there are some few exceptions. If that won't work, then you need to reverse your choice, right? Another nice general principle to apply for choosing the u is that a good choice for u would be those functions which has higher order derivative that becomes zero, right? And I guess we have seen why is that useful whenever or its usefulness is much more apparent if we're doing integration by parts using a tabular arrangement, right? So let's see. Let me go over the questions that was sent earlier to wrap up integration by parts. So I label it additional problems so that the numbering here don't correspond to the questions in the worksheet. So let's start with, say, a definite integral. The integral from 0 to 1 of x ln x plus 1 dx. Here, u substitution won't work because your prime candidate for the u substitution should be ln of x plus 1. But if you let u to be ln of x plus 1, the du required for the u substitution to work is 1 over x plus 1. And clearly, you don't get that in this particular integral, right? Another complication for this problem is that you are considering, or you are computing an indefinite integral. We're computing for a definite integral. And it might be very messy if we will keep track of those changes in the bounds of integration, because remember, once you change the variables, you need to change the bounds. So what I'll do here is to consider the indefinite integral first, find an antiderivative, and then use the first fundamental theorem of calculus. So here, I'll start my solution by saying I'll consider the indefinite integral first. I'll forget for a moment the bounds, and then remember isolate. All right. So let's see where we are at. So the first factor x is algebraic, and the second factor ln of x plus 1 is logarithmic. So in our mnemonic, L precedes A, so we'll begin with, we'll take U to be the logarithmic function, and whatever is remaining would be our dv. So that would be x dx. And then we'll compute for du. So the du is, the differential of u is just 1 over x plus 1 dx, right? And then v would be equal to x squared over 2. Okay, so far? So once you decided what goes as u and dv, then you compute for du and v because that is required in formula number 1. So by integration by parts, we'll see that this guy is equal to uv. So I'll just apply formula number 1. So this is x squared over 2 times ln of x plus 1 minus integral of v du. So that's going to be x squared over 2 times 1 over x plus 1 dx. All right, and we're hoping that the integral on the right-hand side is much easier to evaluate than the left-hand side. And true enough, it's just a rational function. No ln's are there, so we're expecting that would be easier. But it could be a little bit tricky, so let's see. Let me just rewrite and simplify the integral. So I'll just take the 1/2 out. So I'll have x squared over x plus 1 dx. All right. Now, the crucial part at this point would be to integrate this. And here I can use a u substitution. All right. So here I can let u to be equal to x plus 1. So that will mean du will be equal to dx, right? So this guy, let me just copy this over. X plus 1 dx can be rewritten as, okay, we'll have a du here. X plus 1 will just be u. But look at this. We still don't have the right substitution for x squared, right? But if we go back to our substitution statement here, we can see that x is actually equal to u minus 1, making x squared equal to u minus 1 quantity squared, right? So that means the last piece of the puzzle here is to find the right substitution for x squared, and it turns out that that is u minus 1 quantity squared, okay? And then we expand the numerator, so it's going to be u squared minus 2u plus 1 all over u du. And then we can divide do the division term by term, because this is the good thing about this particular form, because the denominator happens to be a monomial, so we can simply divide all terms in the numerator by u. So we'll have u minus 2 plus 1 over u du. This is one thing that we cannot do at this integral, which I still see a couple of students did in the homework or in the exam. What they did is to mistakenly write it as x squared over x plus x squared over 1. You cannot split it up because the denominator is a sum. You can only do the splitting if the numerator is a sum and the denominator is a monomial, just what we had over here, right? So that's why we were able to break it up. And so if we integrate, this is u squared over 2 minus 2u plus ln of the absolute value of u plus the arbitrary constant. Let me call this C1. Okay. And then I'll plug this into this form we have here. Let me just copy these things over. So this guy is equal to this. Right? Okay. But we already knew that this integral over here is equal to what we computed earlier. So it's going to be u squared over 2. Oh, I'll just revert to the original variable. Remember, u is x plus 1. So this would be x plus 1 squared over 2 minus 2x plus 1 plus ln of the absolute value of x plus 1, and then I'll put the arbitrary constant c over here. Okay, and you see how easier it is if you will break the problem down into several components and then just put them back together when you're ready to have the final answer. All right, so everything good? I know this is a long solution, but I hope all of the pieces are clear, and then you'll just to put them together into the final answer. Okay. Now remember, the original problem is a definite integral. So remember, we were told to evaluate this from 0 until 1, I guess. Let me just see. Okay, yeah. And then here we have an antiderivative. So we'll have x squared over 2 ln of x plus 1. And then I'll just distribute this. I'll have 1 over 4 x plus 1 squared. Kindly check my arithmetic here if I'm doing things right. You know, my arithmetic is a little bit sus, but anyway, x plus 1 minus 1/2 ln of absolute value of x plus 1, all evaluated from 0 to 1. Okay, so let's plug 1 in. Plugging 1 in, we'll get 1/2 ln of 2 minus 1/4 times 1, I guess that's 2 squared, plus 2 minus 1/2 ln 2. Minus, let's plug in 0. So the first term goes to 0, second term goes to minus 1/4, and then we'll have 1, and then I'll have minus 1/2 ln of 1. Good? And let's see what happens here. I have a 1/2 ln 2 here. I have a minus 1/2 ln 2 there, so they cancel each other out. This guy becomes -1 because of the negative sign there. So let me just write that as -1. And then I have a 2, so the first term simplifies to 1. Minus what happens to the second term or the second group. ln 1 is 0, so this is 0. So we'll have minus 1/4 plus 1. That's positive 3/4. So this will become, yeah. So this will become 1/4. So the final answer is 1/4. Yeah, so said this is this is very similar to question number 1 that you sent. I guess the only difference is that the function inside the ln, I made it x plus 1, but in the problem you had ln of 2x plus 1. So yeah, but this is the process, and I hope this will help you in solving that. I just wanted to change it a little bit so that you will still be forced to rewrite the solution. There's just a there's just a constant inside your ln. You have 2x plus 1, but the process is the same. So I just want you to take care of those constants. But yeah, this process perfectly applies. All good? Anyone has a follow-up question? I know that problem is a handful, so I guess the trick there is to break it down into several pieces. If you think writing it all over again will make the solution complicated, then solve it piece by piece so that you can track everything down properly and then just put them together in the end. Okay, no questions, guys? I guess that's from the homework, so I hope that you'll get the right answer when you do the homework later. Okay, so if there are no other questions there, so let me try another one. It's still under IBP. Similar to what you sent, or actually I think Michael, Arsalan, and Usosa sent a very similar problem. You had, I think you had sine of ln x or cosine of ln x. I'll take it up I'll take it a notch higher, and say I'll have hyperbolic sine of ln x instead. But the process is the same, even if you have sine or cosine. This is just a little bit more, a little bit. It's not a little bit difficult. It's just I changed the function, but this process will still work even if you just have a sine or cosine, right? So I guess here, u substitution definitely won't work because again, if you will let u to be equal to ln x, then du should be 1 over x. And there is no 1 over x that we can find in the integrand, okay? So that means I don't have any choice but to use integration by parts here. And in the integration by parts, I don't have any choice but to take u to be equal to the hyperbolic sine of ln x. And then dv is whatever that remains. It's just a dx, right? Of course, I hope you see why, obviously, I cannot pick dv to be equal to the hyperbolic sine of ln x. Because if I pick that as my dv, I need to integrate that in order to find v. And now you're back to the original problem, which is difficult to do, right? So there's no other choice but to let u to be that hyperbolic function. And remember, the next step is to compute for du, which is a hyperbolic cosine of ln x all over x dx. Remember here, you need to apply the chain rule, right? And then v will just be x, all right? So applying integration by parts, we get hyperbolic sine of ln x dx is equal to uv. So x hyperbolic sine of ln x minus integral of v du. We're crossing our fingers here. We want this integral to be easier to evaluate. So we'll have x times hyperbolic cosine of ln x all over x dx. All right. Then we simplify that the integrand. So I'll have this, okay, hyperbolic cosine of ln x. But unfortunately, it turns out that this integral is not elementary in form because we don't have a formula for the integral of cosh ln x. And you see that this is a bit similar to the original problem that we had. So I guess this is one variation of the integration by parts, wherein if we cannot get an elementary form for the current integral, we're hoping that at least it will go back to the original problem. So we can perform a trick that I will show later, right? And I expect that the next iteration of integration by parts will give me something similar to the original integral given, the hyperbolic sine of ln x. Because I have a cosh here and I expect a nice form for its integral after doing IBP. So what I'm trying to say there is in the second integral, okay, in the integral in the right-hand side, okay, I will take u to be equal to hyperbolic cosine of ln x, and dv would be dx. Again, du will be a hyperbolic sine of ln x over x, and then v will be x, right? And then that integral, okay, maybe I'll write it here. Our original problem, hyperbolic sine of ln x dx. First IBP told us that there is an x hyperbolic sine of ln x over here. And then minus this quantity over here, minus. Now I want to know where this is equal to. But the second application of IBP told us that that integral can be written as x cosine of ln x. That's the new uv minus integral of v du. So that would be minus integral of hyperbolic sine. Sorry, let me do it step by step. So we'll have v du, so we'll have x times hyperbolic sine of ln x all over x dx. I forgot the dx over there. And that's what we have here. Okay. Oh, I guess there's a problem here. Yeah, my bad. This is not what I intended the solution to be, because you'll see that what is the problem here? I was hoping that I can transfer the integral to the other side, but it appears that if I do that, I will have the integrals will cancel each other out. So probably I should have stuck with sines and cosine instead of showing off and using hyperbolic sines and cosines. And this is what this is what is happening whenever I try to do something on the fly. So yeah, is it okay if we forget about the hyperbolics for a moment here? Sorry about that. I should have stuck with sines or cosines. And I'll explain why I had to do this. But yeah. Instead of hyperbolic sine, it's quite embarrassing, but let's just try sines. Okay, so everything will be sine here. And this is, you know that the meeting is live because I need to make this this changes on the fly. So, okay, sine, this would be sine. And then this would be cosine. And then this is sine. And then this is cosine. And then now here, I'll have cosine here. Oops. And then instead of a sinh, I'll have a negative sign over here. Okay. Okay. That cosh will be gone. But here I will have what? I'll have a negative sign here. And that negative sign there turns out to be very crucial. That's why this method won't work if it's an hyperbolic sine of ln x. I should have expected that, but yeah, we're doing the meeting live, so this happens. But anyway, so let's simplify the left-hand side. So x sine of ln x, oops, minus x cosine of ln x. And then I'll have a minus sign there times a negative there. So that's going to be positive, but there's a negative sign there. So ultimately, we'll have negative integral of sine ln x dx. All right. Okay, is this good? I hope I didn't forget to change anything here when I did the transition from sinh to sine. Okay, and at this point, we notice that, oh, I have integral of sine ln x here. Okay. And then I also have the integral of sine ln x over here on the left-hand side. And whenever that happens, when in one iteration of IBP that you perform, you go back to the original problem, then what you can do is transpose this thing into the right-hand side or into the other side of the equation. And then you can combine those terms. It wouldn't be a plus Arsalan because here I have a negative sign here, right? From the du, multiply it by the negative sign from uv minus vdu, right? So that becomes positive, but it is inside a big bracket, so there's a negative sign over there, so it will become negative. And that was the problem I had if I stuck to hyperbolic sign. Because if it was a hyperbolic sign, so I don't get a negative sign here, this will be a plus. If I transfer that to the right-hand side or to the left-hand side, this will become 0, and I don't get any any integral left, right? So that's why I needed to change the problem. So here I'll have a 2 hyperbolic sine of ln x dx, right? After transferring that, negative integral becomes positive integral when you transpose it. So we'll get 2 on the left-hand side. Then this will be x sine of ln x minus x cosine of ln x, right? And then I'll put an arbitrary constant, say c1 over here, all right? Because all the integrals are gone from the right-hand side, so just to remember that there's an arbitrary constant there, I'll put the c1, right? And then I'll divide both sides by 2 to finally get the expression for the integral of sine ln x, right? Because remember, this is what we are computing for, right? From the beginning. So I'll simply divide both sides by 2. So I'll have x over 2 sine of ln x minus x over 2 cosine of ln x. And then supposedly I'll have c1 over 2. But c1 is a random constant. You have a random number divided by 2. That will again be a random number. So I can just call it c. Okay, and this is again one variation of integration by parts, wherein along the application of IBP, you again meet the original function on the right-hand side. So what you can do is to transfer it to the other side and divide both sides by whatever constant is there. All right, is that clear? I guess this appears in one of the electronic quizzes. So another variety of this problem is you have hyperbolic cosine. Sorry, you have the integral of cosine ln x, but this is the process. Okay. All right. So there's another interesting problem that was sent. I don't know, guys. Where did you encounter this? Was this from the quiz involving integration by parts, or from the quiz about powers of trig functions? I'm not familiar with the quiz number, sorry, but I guess this is still under IBP, but you can also categorize it under section 8.2, which is about the powers of trig functions. So I was thinking whether to answer it at this point or defer it for next meeting. But since this was asked multiple times in the chat, so I decided to do it here. Going back to Michael's question before proceeding to problem 3, what was du and v for this problem? You mean problem number 2, Michael? If you're referring to problem number 2, I applied IBP twice. So here, for the first iteration, I let u to be equal to sine ln x because I don't have any choice. And then dv is dx. And then I did IBP again, but I had cosine of ln x in the integral there. So I need to do integration by parts one more time. But in that integration by parts, I don't have any other choice again but to choose the cosine ln x to be the u. And then dv is always dx. Okay. All right. So now we go to integral of secant cubed x dx. So this is one example wherein you can, if you have a power, you can split up the power into several parts and then choose the u and dv coming out of it. You will see this again when we discuss powers of trig functions, when we go to powers of secants and tangents. And this is one case that I would have introduced later, but we'll do it right now. So the trick here is to write this as integral of secant squared x dx, all right? And why do I choose to write it this way, right? But I hope you agree that these two are equal to each other, right? So I just isolated the secant, and then there's a secant squared left. Remember, our choice for u is something that can easily be differentiated, and dv is something that can easily be integrated, right? Of course, secant cubed cannot be integrated properly. The integral easily, rather. The integral of secant is ln of secant x plus tangent x. That doesn't look good. It's a very messy expression. But the integral of secant squared turns out to be nice, right? The integral of secant squared is simply tangent x. And I'm betting that that would be helpful here. So that's why I decided, okay, I'm going to isolate secant squared x. and put it together with dx for the choice for db. Because again, dv should be an easily integrable function, right? And whatever remains would be my secant, would be my u. Okay, you compute for du, you'll have secant x tangent x here, then your dx there, and then v would be the integral of secant squared x, or an antiderivative of secant squared x, which is just tangent x. Good? So if you apply IBP, the integral of secant cube x dx is equal to uv. So you'll have secant x tangent x minus integral of v du. So you'll have secant x tangent squared x dx, right? So I just went on with the multiplication of v and du and got this. Good so far? Okay, now let's worry about this integral over here. I guess here I can apply a trigonometric identity. I can let note that tangent squared x, okay. Maybe I should write that down here. Recall that 1 plus tangent squared x is equal to secant squared x, right? So what I can do is have the integral of secant cube x dx written this way: secant x tangent x minus integral of secant x times the tangent squared x can be written as secant squared x minus 1 dx, right? So this is a useful trig identity. And then I'll simplify the integral. This is minus integral of secant cubed x minus secant x dx. All right. And the reason why I decided to use this identity here is that I recall that, okay, here we're computing for the integral of secant cubed. And here we have repeated that integral over there, right? So you will have a secant cubed x again after applying an integration by parts. Or more explicitly, you can rewrite it as secant x tangent x, and then I can split this up into two pieces. I'll have integral of secant cubed x dx plus integral of secant x dx. All right. And again, this guy is a repetition of the original integral, right? So you can transfer it to the other side. And doing so will give us twice the integral of secant cubed x dx is equal to secant x tangent x plus, now what is the integral of secant x? Now, if you remember from the formulas, I'm not sure if it's from Cal 1 or early Cal 2, the integral of secant x is ln of the absolute value of secant x plus tangent x plus the arbitrary constant c1. And then we can divide both sides by 2 to get this. 1/2 secant x tangent x plus 1/2 ln of the absolute value of secant x plus tangent x plus the constant c. All right, all good? I guess in the online quizzes, you have a constant in front of the secant cube in the problem, but it's not a big deal. You can just rewrite the solution and take into account that constant. Okay, is that good, everyone? Any follow-up question? Yeah, Herson, that's right. You can do that and then just multiply everything after. That's fine. I did not intend to say that out loud so that you will be forced to rewrite the entire solution. So, but yeah, that's the trick there. But I hope the process makes sense because you might encounter this again because in section 8.2, this is one particular case of a power of trigonometric functions. Okay, any question about IBP? If there's none, oh, I think Arsalan sent a question. Yeah, probably I'll outline the solution to Arsalan's question. He sent this integral of x cubed cosine of 6x squared dx. There are several ways on how you can answer this one. Oh, she went over that? Oh, okay. Yeah, you could have told me that so that we went ahead with a different example. But yeah, when cases like that, when I'm answering a problem that a problem that was already discussed by Dr. Almas in the lecture, kindly let me know so we can answer a different one, so that we will not be wasting time going over the same example again. But nevertheless, it's nice to re-emphasize the point, but we could have answered a different problem. Okay. All right. So in this case, again, there are several ways to answer this. But what I suggest is, of course, here you have an x cube outside. So probably we'll need to apply integration by parts here 3 times. And that could be messy. But what you can do here before applying integration by parts is to use u substitution first. So I will say let w. I don't want to use u here in the substitution because you'll use u and dv in the integration by parts, so I'll use w here. So I'll let w be equal to 6x squared. And so dw will be equal to 12x dx. So the original integral, I can actually write this as I need a 12x dx to get the dw, so I'll put that there. So I should take away that 12 that I introduced out of the blue. So I have a cosine 6x squared over here. And then I took the x out of the x cubed, so there would be an x squared left over here. Okay. And so that means this would be integral of, okay, 12x dx can be replaced by dw. And then I have cosine of u here, right? And then I have an over 12 over here. But from this expression, I see that x squared can be written as w over 6, right? So x squared is w over 6. So that means this is 1 over 72 integral of w cosine of w dw. And here you only need to apply IBP once by taking u to be equal to w and dv equal to cosine w dw, right? Because of isolate. 12 came from the u substitution because here, remember, I'm letting w to be equal to 6x squared. So that means dw is 12x dx. So that's why I need a 12x dx to get the dw. So that's why I have here. But you're right, 12 came out of the blue, so I need to take that 12 away so that I go back to the original expression. So I divide it by 12 again. So there's an excess of 12 in the denominator. Or another way of looking at it, maybe you're more familiar with this, is here you can write x dx equals dw over 12. So this x dx over here will be replaced by dw over 12. All right. Okay, so I guess you can do the rest of the solution here. Okay, let's try, maybe I can introduce powers of trig functions. So is it fine? We put IBP at the back burner for now. Let's try worksheet 9. Okay, there we go. And this is about integrating some powers of trigonometric functions. And the thing here is that here we will be taking advantage of trigonometric identities and actually use substitution again. But the choice for the method will depend on the parity of the powers. When I say parity, it is the exponent being odd or even, right? So we will be discussing here powers of products of powers of sines and cosines. So sine, say sine to the m, cosine m to the x dx, right? And then we also have powers of secant times powers of tangents. Sorry, this is an n. But this second case is similar to the integral powers of cosecant m, powers of cosecant and cotangent m dx. So basically, we are dealing with this powers. Let's start with powers of sines and cosines. So basically, we can reduce this case into two subcases. Number one is when both either m or n is odd. Or the case is when you at least have one odd power, right? So if you see that you have a product of powers of sines and cosines, and one of them happens to be odd, so what you'll do is to reserve a factor from the odd power, and you reserve it as you reserve it for the du. Okay, so if say m is odd, so you have sine cubed, right? So reserve 1 from sine cubed, so you will have sine squared times sine. That lone sine factor that you isolated will be reserved for the du. So if that will be the du, then you know that your u should be cosine because you are reserving the sine for the du, right? And then write the remaining power. So what remains would be even power. Because remember, one of them is odd. You take 1 from that odd power, so you will have an even power left. So that remaining even power left should be written in terms of the other function using the Pythagorean identity sine squared x plus cosine squared x equals 1. Now I realize that is a handful of a sentence there, but essentially, when you see something is odd, isolate one factor from that odd power, right? So we'll now have an even power times single factor. That single factor will be reserved for the du, and then the remaining even power should be used or should be expressed in terms of the other function using this Pythagorean identity. And as always, maybe it is easier if I'll show you an example, but that's the idea here. And if both are even, obviously you cannot apply the previous asterisk because that requires at least one of them to be odd. When both are even, then we need to use the half angle identities. Okay. Maybe we won't have time to do secants today. So here what I mean about half angle identities is that sine squared x is equal to 1 minus cosine of 2x all over 2, and cosine squared x is equal to 1 plus cosine 2x over 2. So these are identities that you have met in algebra and trigonometry. Okay. Now I have 5 or so minutes, so let's apply this to asterisk here and look at some problems. Let me try problem 4. Again, let me know if you have already considered problem 4 in the lecture. Hopefully not, because if that's the case, then I should use higher power here, which will entail a lot more algebraic manipulation, right? But so here, obviously, you cannot do a simple U substitution at this current form because you have high powers of cosines and sines. But so the first thing is to look at the parity of the powers. Cosine has an even power, has an odd power. Sine has an even power, but the good thing here is that one of them is odd. Remember what I mentioned earlier? If you have an odd power, reserve one of those one of those powers, one of those factors to be your du. So I have an odd cosine power here. So I'll reserve one of them for the du, right? So I'll put that aside. So instead of a cosine cube now, I'll have a cosine squared here times sine to the 4th x. All right. This is what I meant by reserving one factor from the odd power for the du, right? So having said that, I know here that I will let u to be equal to sine x. Because if I do that, then du will be equal to cosine x dx. So I can use the factor that I set aside earlier from the odd power. All right.
I have a question. Would
Sure.
it be easier to like do it like sine to the square? Or would it make it more difficult, the u?
Yeah, that's also fine. Yeah, though I will expect that you have already used that in the lecture.
Okay.
So yeah, I just want to illustrate what I mentioned, what I wrote earlier. So yeah, but of course there could be other methods that you can apply, right? So okay, so here, but I want everything to be expressed in terms of u, right? So this guy will become my du. No problem about this. This will be u to the 4th. But the problem here is the cosine squared, right? But this is why I want to only have even powers of sines and cosines left, because now cosine squared x, as I've mentioned above, you can use Pythagorean identity here. Remember, cosine squared can be rewritten as 1 minus sine squared x using Pythagorean identity, right? And this is good because 1 minus sine squared would be 1 minus u squared, right? So therefore, the original integral can now be written, sorry, as integral of 1 minus u squared, right, times u to the 4th du, which is now a polynomial. So you can simply perform the multiplication first and then integrate as if you are just integrating a polynomial. So this is u to the 5th all over 5 minus u to the 7th all over 7 plus the arbitrary constant c. But remember, we need to go back to the original variable. Here we let u to be equal to sine x. So this is sine to the 5th x over 5 minus sine to the 7th x over 7 plus the arbitrary constant c. All right. Any question about that? So I hope that you see beyond the formula or the bullets I wrote earlier, because this is nothing more but the clever use of trigonometric identities and the U substitution. So actually, I just wrote that formula for this lecture, but whenever I'm doing integration, I usually think of what would be the appropriate way to get a U substitution. So I just took extra time today and to summarize my thought process in order to write that that method above. But this is what you can do whenever at least one of the powers is odd. If both of them are odd, then you can still do this, right? So say if you have cosine cube x, sine cube x dx, you can choose whether to isolate a cosine or a sine. That doesn't matter. So as long as you take one from an odd power and then reserve that for the differential du, right? So unfortunately, I don't think I have time to illustrate the case when both are odd, but I guess we are still, sorry, if both are, if both are odd, but I guess we are still in a good pace because you just started with section 8.3 in the lecture today. So majority of our time on Friday will be devoted on the other cases for trig powers, okay? So as usual, please try the exercises here from the textbook. There are 34 integrals. I guess they are more sufficient here. I guess the challenging problems here involve integrals where you need to apply some trigonometric identities first before being able to write it as a power of a sine or a cosine. So I'll pick some of those for next time, but hopefully we'll see that late. We'll see that. We'll see those problems on Friday. But as always, if you encounter some difficult or some interesting problems from quizzes and homeworks, just let me know. All right. Okay, guys, that's it from me today. So thank you for coming, and let's see each other. Let's see each other again on Friday. All right. Have a good day, everybody.